A little bit more on carbocations. So I like to say there are two fates to a carbocation. And when I say two fates, I mean two ends, two things that lead to the loss of a carbocation. And that'll either be that the carbocation gets attacked, or the carbocation can lose a beta hydrogen. And these really are references to the two carbocation reactions we've seen, either the SN1 or the E1. Now, when I'll ask about what happens to a carbocation, students will often throw in a third fate. Sounds mysterious. Third fate. What could that be? Well, carbocations sometimes will rearrange. Now, I don't consider this to be a true fate of a carbocation, because when a carbocation rearranges, it forms yet another carbocation. So we're not talking about the demise of a carbocation. It's just a change in the carbocation. Regardless, it is something that happens to carbocations. So in a sense, it's kind of a fate. So what does this look like? Okay, let's say we have this halide, and we treat it with let's treat it with ethanol just to mix things up. So no nucleophile. We're not going to do an SN2. We got a secondary halide. It's kind of crummy, but we can make a carbocation out of that. Note that we also don't have a base in here. We don't have an alkoxide or something. So we're not going to do an E2. No SN2, no E2. This is possibly going to be some kind of substitution, SN1 substitution. So if this halide does leave, we will form a secondary carbocation. Now, secondary is not as good as a tertiary, but the fact is, you got a secondary halide, you are going to make a secondary carbocation. But wait, this secondary carbocation knows that tertiary carbocations are better. And what can happen, and it most often happens with hydrogens, there are other variations of this, but what happens is you can undergo a rearrangement where this hydrogen, with its electrons, with its bonding pair, will hop over to the carbocation carbon. And that's the mechanism for it. Remember, these mechanisms, we're moving electrons. So the arrow starts where the electrons are and shows where the electrons finish. So, tell you what, let's draw in the hydrogen that's already there. So now instead of having one hydrogen on that starred carbon, we have two hydrogens. But that means this carbon, where that dot is, something has to change, and it's lost electrons. Well, the carbocation will now reside there. And so what we've done is we've gone from a less stable secondary carbocation to a more stable tertiary carbocation. This is a rearrangement. Rearrangement. It's called a hydride shift. A hydride is H minus. It's a hydrogen with a lone pair. And what's happened is the hydrogen with its bonding pair has moved. A hydride has moved. I will often just write rearrangement RAR because it's a lot faster. So then, once you get to tertiary carbocation, the question becomes the same. What are the two fates of a carbocation? Well, this new carbocation could either get attacked or lose a beta hydrogen. And we have ethanol in here. Ethanol will attack our carbocation. And quickly finish this off. That's a charged species. We need to neutralize this. The best base at hand is our ethanol, and we get this substitution product out of it. So you might look at these conditions and say, oh, of course we're going to get a substitution. I'm going to replace the chlorine with ethanol. The fact is, this is not observed. It's not observed because as we form our carbocation intermediate, it rearranges to make the tertiary carbocation, and then that tertiary carbocation ends up getting attacked. So here is our actual product over here in the bottom right. It arises from carbocation rearrangements. Be on the lookout for rearrangements. If you ever form a secondary carbocation, be aware that it may be possible to form a tertiary carbocation. Note this hydrogen, if it moves, it's got to be next door. It can't be on the other side of the molecule. It can only hop over one carbon. So don't go flinging hydrogens all over the molecule. It only goes from a next door carbon.